Okay. So today I shared with you the notes that you'll see up here. I thought it would just be easier. There's a lot of terminology I just wanted you to have, and I didn't really want to, I wanted to make sure you had it, okay, rather than you having to write it down all the time. So the notes that you're looking at here are going to be the same notes that you're looking at on the screen, and you're just going to fill certain things in, right? That's kind of the idea behind this. I thought it would help save us time. Now, we are starting a chapter on hypothesis testing. We're going to cover it in kind of like a combination of sections 10.1 and 10.2 are going to be covered today. And then Wednesday, we'll cover the rest of 10.1 and 10.3. All right, so we're kind of introducing it a little bit. We'll do a little bit of the proportion, hypothesis testing on proportions, and then finish it up, hypothesis tests on mean on Wednesday. And this is the last chapter that we actually cover as far as inferential statistics is concerned before you have a test over this material a week from this coming Wednesday. So the test over this material should be next Wednesday, okay? All right, and what we're focusing on in the last chapter, chapter 9, we were talking about confidence intervals, right? And kind of getting this interval that had the where we projected the population's proportion to be at. We don't ever know what the population's proportion is truly going to be, but we have some wiggle room, we have some tolerance, if you will, some margin of error, we call it, around our sample for what we believe the population to be. Right? That's just a confidence interval. Now, another way of talking about strength of evidence, in addition, I would say, to our confidence interval is this chapter here. And this is our chapter on what we call strength of evidence. When we're thinking about strength of evidence, what we're talking about is this idea where we want to know how unusual our observed statistic would be. In other words, how unusual is our sample statistic, the one we would create using our experiment or simulation, right? How unusual is that statistic compared to what we think the population's value is supposed to be? So we are estimating this strength of evidence. How unusual is it? And we've used that language since we've been talking about empirical rule back in chapter whatever that was, 3, I think, or something like that, 2 maybe even. So that's the premise behind this. So our observational value or the observed value is really just our sample statistic, right? It would be our p hat for a proportion, or it would be the x bar for a mean, right? So keep that in mind. We are always taking our sample and we are trying to determine, in this particular chapter, we're determining how unlikely is it for me to get these results if I know or if I believe the population to be this, okay? All right, so it says under many repetitions, how unusual would it be? Now, something to consider, and I would encourage y'all to get highlighters out, colored pencils, whatever it is that you need to take notes with, and highlight, circle, underline anything that you can in these notes, because there's a lot in it. When we're talking about our strength of evidence and this idea of our observed statistic, and let's just focus in on p hat for a minute. In other words, if our observed value, p hat, is unlikely to have occurred, right? If your box of M&Ms, your proportion of orange M&Ms, if it was unlikely to occur over many repetitions, then what we say is we have strong evidence against the claim that Mars says that 20% of them should be orange. So if it's unlikely for our proportion, our sample proportion to occur, then we say we have strong evidence about the claim of the population. About the claim of the population. And our hypothesis testing is always taking our sample information and it is basing it on the claim of the population. That's where the inference comes in, right? We are inferring something about the population. And if our p hat isn't likely to have happened, then whatever was being claimed about the population is not true or is unlikely. So if our observed value if the proportion of M&Ms in our box was not something unusual, right? If I got 23%, Michael, you got 19%, Erica, you got 22%. If that's not an unusual value, then we would have to say, okay, well then the population's claim of 20% on average of every box is plausible. It doesn't say that it is exactly 20%. It just says that that number of 20 is plausible, or whatever our population's parameter is. Remember, a parameter describes a population and a statistic describes a sample. Keep remembering that, right? Population and parameter go together, statistic and sample go together, okay? Just like we talked about at the beginning of this semester. So when we talk about our hypotheses, we all know what a hypothesis is, right? Okay, from science class, a conjecture about what we think it is. Well, in our hypothesis is our statement regarding the population. Remember that. It's a statement regarding the population. And we have two hypotheses. We have what we call our null hypothesis, which is denoted as H sub 0 or H sub naught. That's what that 0 would be. H sub naught is our null hypothesis. This is always going to be the statement that we assume to be true. The null hypothesis is always going to be a statement about equality or something that is true. That's the part we assume to be true unless otherwise unless otherwise stated, unless we find something else. Now, our alternative hypothesis, which I have both of those listed up there. I usually use the H sub A for alternative. I've also seen it written as H sub 1. So anytime you see those, that would be referring to the alternative hypothesis. The alternative hypothesis is typically what researchers think is true. This is the part where we think it's true. It's what we're trying to show. It's what we are trying to prove. Okay. Now, if we put this in terms of our proportion, our experiment that we just had on confidence intervals with our orange M&Ms, our null hypothesis would look something like the proportion of M&Ms in a bag of candy is 20%, right? That's our null hypothesis. That is a statement about the population's parameter. That's the statement that Mars said was what they thought, right? That the proportion of orange M&Ms in a box or a bag of candy is 20%. This is what we expect the orange M&Ms, or we would expect orange M&Ms. We would expect, that's a poorly constructed sentence, isn't it? We would expect about 20% of the orange M&Ms, a box of M&Ms, to be 20% in the long run. Alternative hypothesis. This is what we would make the claim about. All right. This is about what we would want to show, that the proportion of M&Ms in a bag of candy is more than 20%, perhaps. Maybe that's what we wanted to show. Okay. Maybe you believe, no, I don't really think it's a 20%. I think it's more than 20% in a bag. Right? That's where the alternative comes in, and that's generally what we are trying to show. And we're going to try to see how can we take what we want to show and test it in essence against what the population says is what we think is true about the population. So these hypotheses represent, once again, information about the parameter, that long run behavior of over and over and over doing something, right? That probability of something happening. The information of our hypotheses represent the long run parameter and not the statistic. So the null and alternative hypotheses are always written in terms of the population's parameter. If you'll notice what I have there in the null and alternative hypothesis for the candy, we are referring explicitly to what Mars' claim is for the proportion of orange M&Ms. Not anything about what our samples provided, okay? That's the null. That's the hypothesis. Okay. So let's look at this idea right here, okay? And kind of see how basically everything we've done so far, how it is all related to what we're fixing to talk about. So how many of y'all have ever played the game rock, paper, scissors? How do you play it?
Like you just say rock, paper, scissors, shoot, and you can pick rock, paper, or scissors.
All right, so one of you would win because the other would crush together, right? So what? Rocks crush scissors, paper covers rock, scissors cut paper, right? Okay, so there's 3 outcomes when you play rock, paper, scissors, right? Because you can choose any of those 3, a rock, a paper, or a scissors, and then depending on how it's lined up would depend on who would win. Now, you could tie. Let's go with 3. Keep it simple, okay?
Pretend
the
we're
game-
not gonna.
Huh?
Pretend we're not gonna.
We're gonna pretend we're not gonna tie right now. All right, so is the game of rock, paper, scissors fair? All right, so a 2009 article published in College Mathematics Journal found that players, particularly novices, tend to not prefer scissors. Suppose that we investigate this tendency with a friend who hasn't played the game before. I don't know who that would be, who hasn't ever played that before, but we're gonna pretend that we find somebody who's never played it. And then after 20 rounds of play, you find that the friend chose scissors 4 times. Okay, that's where we're starting. Now, what type of variable are we looking at here? What's changing each time? Each time you play, what's changing? The outcome of rock, paper, or scissors, right? So the variable would be a rock, paper, or scissors. Okay, so we're going to claim that the variable in this particular case, is choosing scissors, right? Because it specifically says after 20 rounds of play, your friend chose scissors 4 times. It doesn't really tell you anything else about how many times they chose any of the other options, because the question is whether or not it's fair, and people tend to not prefer scissors. So we're going to focus in on scissors in this particular case. And if the outcome is whether or not you choose scissors, right? What type of a variable would that make it? Quantitative or qualitative? It's qualitative because it's categorical, right? So this would be qualitative. In fact, it would be binary, right? We're looking at the fact of we only want to know whether or not scissors was chosen. So it's either scissors were chosen or not chosen, which makes it a binary or 2 possible outcomes in this particular case is what we would call it. Okay. What is the parameter in this case? What is the probability of getting scissors in the long run? We've already said this, but what is it? What's the probability of choosing scissors in the long run?
1 out of 3.
1 out of 3, all right? So the parameter, remember parameter talks about the population, right? In the long run, you have a 1 in 3 chance of choosing scissors. Do we all agree with that? Yeah? Okay. And notice that I've already identified a variable for my parameter. We're talking about a proportion here, so we're going to use lowercase p. Lowercase p, no hat, no nothing, right? That indicates parameter population variable. So what we have here is the parameter is going to be that you have a 1 in 3 chance of choosing scissors in the long run. All right. Now, what's our statistic? What is the statistic supposed to describe? The sample, right? The statistic is supposed to describe the sample. So what is our statistic from the results of these games?
4 out of 20.
Okay, so we have 4 out of 20. Remember, so p hat gonna be 4 successes out of 20 trials, or we'll just cut that down to 0.2. So what we have here is, we have the long run probability of choosing scissors in this game is a 33% chance. We had somebody who played the game for 20 rounds and they chose it 20% of the time. All right, make sure you understand the difference. The long run probability of choosing scissors is 33%. 20% represents what happened in one particular experiment. Okay, one particular trial. Okay, now so it says, suppose that we decide to investigate the tendency, suppose we decide to investigate this tendency. The tendency is that people do not prefer scissors, right? They would choose scissors less time, right? All right, so the null hypothesis, when we state our null, when we try to write our null and our alternative hypothesis here, in our null hypothesis, notice it says, this is how we would state it. You're all going to be asked to state these yourself. People playing rock, paper, scissors will equally choose between the 3 options, or in other words, that the null h sub 0 says that the population parameter p would be equal to 1/3, right? They would choose equally between the 3 options. That's the first sentence right there. That's our null. The null hypothesis is always a statement of equality. Notice here we have an equal sign, right? And we're choosing equally between them. And this is what we're assuming true. We know that if we played this game, when we talked about probability back in chapter 5, you have 3 possible outcomes. Then scissors is only one of those possible outcomes, so you would have to have a 1 in 3 chance of choosing scissors in the long run. The alternative is where we are trying to prove or show or, discuss, I suppose, right? What we want to find. It says they tend to not prefer scissors. So people playing rock, paper, scissors will choose scissors less than 1/3 of the time. Less than 1/3. So our alternative says, okay, then the long run proportion's got to be less than 1/3 if we're just talking about scissors. So I want you to notice that the null hypothesis is about, so in both of these, we're using something about the population parameter of 1/3, right? Both of them are using 1/3. The null hypothesis is always going to be that statement of equality, the one that we assume to be true. The alternative is what we're trying to show. That's the strength of evidence. Can I show that people are less likely to choose scissors? That's how the test is brought up. So these are the 2 things that I'll be asking you to do. Not only write for me the null and the alternative hypotheses in words, but also show me in symbols. So by symbolically, I'm talking about the H naught is colon P equals 1/3 and so forth, right? So I've got symbols and I have words. Okay. So what I want us to do, everybody go to that app that I had you hopefully look at. Okay. He does this, our author does this in the textbook, but I think that it's, I'm a little bit more familiar with this applet. I kind of understand this one a little bit better than the ones that he does in StatCrunch. So we're going to do our simulation here on this one, as opposed to doing it in StatCrunch. We're going to move over to StatCrunch to talk about, to actually run the hypothesis test. So I only want to use this as an illustration in class as to what's happening behind our hypothesis testing. I don't want you to think that this is how you're going to be constructing your hypothesis test in the future. This is just a simulation. Okay. Now, the way that this looks is, I want everybody to, let's see, we're going to come over here and we're going to change this probability of heads. This is actually about the probability of your parameter. What's the probability of getting scissors again? For the populations parameter, what was P? Okay, so we have to put this in as a decimal, so we're gonna put 0.333. And then the game that this person played, and notice as soon as I click someplace else, it changed it to, they use pi, but it's still R capital P. The sample size, how many rounds of rock, paper, scissors did our person play? They played 20 rounds. And then I'm just gonna do this once. I want y'all to just see what's gonna happen here. So if I were to simulate, could I repeat, right? Could I recreate the same round of 20 that this person played, right? And what would be the outcome? Okay, so I'm recreating the same game that they had. Okay, now, there's a lot of times when you're doing simulations where you could use a coin to represent binary outcomes. That would have to be if they were equally likely. So if I wanted to know whether or not people preferred Coke over Pepsi, that would to me be an equally likely outcome, correct? A coin would be a great way to simulate that. In this particular case, even though I only have two outcomes, whether or not someone chose the scissors or not, they're not equally weighted, right? 1/3 of the time you would pick scissors, 2/3 of the time you would pick the other two, correct? So they're not equally weighted, and so in this particular case, you can use a spinner to simulate the process. Okay, so instead of us flipping a coin a bunch of times to simulate people choosing Coke or Pepsi, because they're evenly weighted, I would have to move to this because it is not evenly weighted. And what we have here is we played one game. The results from my simulation said that the successes, right, would be representing choosing scissors. So in my particular case, we had 6 out of 20 repetitions, right? We had 6 out of 20 rounds, in my case, where they chose scissors, okay? So that was mine. All right, so Erica, I'm looking at you. How many did you have?
Successes, 12.
12 out of 20, all right. Erica P, what did you have? 8 out of 20, okay. What did you say, Erica? You had how many?
I had 12 successes.
12, 8, okay. Michael?
8.
8. Okay, do you have yours?
Yeah, 5.
5, okay. Abigail?
4.
4, I've already lost track, but they're not all the same, are they? Okay, Michaela, what you got?
Same as yours.
6, Addison? 4,
5.
5,
7.
7, okay. So in all of our simulations, okay, she had 4, right? Whenever we're doing this, whenever we're looking at this, the start of what we were talking about, whoever we looked at when they did the experiment, they ended up with 4 out of 20. Did somebody in here say they had 4? You said
4 successes.
4 successes out of 20, which would have been the same thing, okay? So if the likelihood of choosing, so what we're trying to say is we're trying to figure out, well, how unusual is it then for the person who ran the original experiment to get the results that they did, all right? Is it unusual for them to get a 4 out of 20, okay, or 20% of the time, all right? That's what we're kind of looking at. Now, I'm gonna hide the spinners because I think you all understand how we can simulate things using spinners, dice, coins. I'm gonna hide those because I don't want to see them again. And I'm gonna uncheck the animation because I don't need to see that either. Now, what we want to know is, okay, a couple of other things we want to click on here. I'm gonna change the statistic to show the proportion of successes. So I want to know the proportion instead of the actual number, right? So I want to know the proportion. And then what we're interested in looking at is how unusual would it be, right, to get a statistic at or less what we started with, that 20%, right? That we said P hat was, okay? So I'm gonna put a 0.2 here. That's kind of my baseline. Remember, that's P hat. That's what we are testing against. How unlikely, how unusual would it be for us to get 20% scissors out of 20 round game? Okay, that's what we're really looking at. Okay, now, because I don't want to look at the spinners 1,000 times and I want to just see what would happen if we did this 1,000 times. Okay, because that's kind of like long run probability. Let's click, let's put 1,000 up there. Under the number of samples, which is the number of repetitions in the game. And if I draw those samples, I end up with something that looks like this. It looks like a histogram, right? In essence, the shape or the distribution of it looks like it's a bunch of samples. And what we have here is in 1,000, I believe that would be 1,002, I'm not really, 1,002 different samples of 20 rounds, okay? I have this distribution. These are the results that we're looking at. Okay. Now, the part that we're somewhat interested in has to do with, if you look under here, do you see the proportion of samples in red? Does everybody see that proportion of samples in red on their own screen? Okay. So in 1,002 different repetitions of this process, my simulation came up with 174 of them had 20% or less choosing scissors. What was y'all's? 155, 154. Actually, what was yours? 155. Michael, what was yours?
158.
58. Michael. Okay, Abigail. Did you see it's the red one, right?
Oh, yeah, I got 0.15%.
So 15, somewhere around 150, something like that. Caden, what was yours?
149.
49. Okay. Madison, what was yours? It's this one down here right underneath the count.
Mine's just saying 0.
Oh, all right. Well, something happened on it. We'll look at that later. Okay. So what does this mean? This means that if we were to simulate this a gazillion times, right? We all ran it actually 1,002 times. So that's 2, 4, 6, 8, 10. 10 times 1,000, right? It's a bunch, okay? And in that many different repetitions, we would expect anywhere between, I think I heard 15, I may have gotten 13 the other day, 17, anywhere between, let's say 13 to 17% of the time, you're gonna have a result that was 20% choosing scissors or less. So is it unusual then for this experiment that this girl did to choose scissors only 20% of the time? Why? Why did you make that conclusion? I completely agree. Because it's more than 5, it happens more than 5% of the time in the long run, right? So it's not an unusual thing to have happen. Okay? And if it's not an unusual thing to have happen, that's what we're testing against. Now, our simulation here is an experiment, right? It's an experiment, okay? We're not gonna always go out and simulate things all the time because that doesn't make sense. And so this number, the proportion of samples that were at 20% or less, which is why it's highlighted red and everything less than that was highlighted red as well on our graph, okay? That proportion of samples that were at P hat or less becomes our P value. All right, that's what a P value is, the probability of getting our statistic, which is P hat, it's the probability of getting our statistic or less that many times, okay? Okay, so moving back to the paper we have here. So this is important. Highlight, whatever, right? Do something to engage your brain so you know you're getting this. The p-value is the probability of getting a result that is either the same or more or less, depending on our inequality symbol. So it's the probability of getting a result that is either the same or more extreme than the actual observation. It is what we use to measure the strength of evidence against the null. Small p values, we've got it in there as to what that exactly is, what constitutes a small p value. But we're kind of generally saying, okay, it was less than 5, if it's less than 5%, it would be unusual to have happen. That's what that's referring to. Small p values suggest that that result would not happen, is unlikely to have happened, and therefore that's evidence against the null. We don't have a small value because ours is not necessarily unusual to have happened, so we don't have any evidence against the null. That's how we conclude it. It can be thought of as measuring also how far our sample statistic is away from the middle under the null hypothesis, which is what we kind of looked at in chapter 8, sampling distributions. Okay. Okay. Let's look at another example here. Kramer's predictions. So a website keeps track of predictions made by individuals in finance, politics, sports, and entertainment. The website kept track of 680 stock predictions by a famed TV financial personality and author, and found 310 were correct predictions. We want to treat these predictions as a random sample. And we want to know, does the sample evidence suggest that this TV personality is correct less than half of the time? So what we're looking at here. Okay. Okay. So let's think about this. What is the variable of interest in this study? Correct predictions. Very good. Right? So our variable of interest in this study would be the correct prediction. And how would you answer that question? Was it a correct prediction or not? It's a yes or no question, right? You either got it right, that would be success. Correct prediction would be success. Not correct prediction would be failure. Okay, that would be qualitative. Okay. What was the goal? What are we trying to look for again here?
To prove that H of A is less than.
All right, so we're trying to wonder, we want to know whether or not the correct is less than half the time, right? Less than half the time, or whether or not he's correct less than half the time. Okay. So now we want to consider what the null and the alternative hypotheses are. Okay. First, it might be helpful to understand, before we get into that, it might be helpful to understand our parameter as well as our p hat. Okay. So we're trying to say, okay, is he correct less than half the time? So we're saying that in the long run, maybe he's only correct. In fact, this is what they're assuming, right? They're assuming to be true that the parameter for the population is 0.5. Flip a coin, in essence, right? And in fact, you could simulate it using a coin simulation method, all right? And then what is p hat in this particular case? What proportion of the time was he correct?
0.456.
So it was 310 out of 680, okay? 310 out of 680, which you said was 0.456, okay. So our null hypothesis would be that this TV personality predictions are correct half the time, right? Our null would be that the TV personality predictions are correct half the time. Meaning H sub naught is represented by P equal to 0.5. And the alternative is that the TV predictions are correct less than half the time. So H sub A is P is less than 0.5. Okay, so two things I want to point out about how I came up with our written statement for the null and the alternative is that in relation to this problem, I'm trying to talk about what the population parameter is believed to be in context to the problem, and they believe that he's correct half the time. So P would have to be equal to 0.5. And the alternative is really a restatement of, like, I didn't have to change very much in there except the less than half the time portion, okay? In a written statement. So I'm really restating it in essence with the different mathematical interpretations, I should say. So let's go back and let's look using our applet that we have. That is really only about simulations. I'm gonna uncheck the spinners just for a minute. So I'm gonna reset everything in here down at the bottom. Reset some of those numbers, didn't reset very much. Part in this first blank, this is, what's the population parameter we just said? Okay. 0.5. What was the sample size that was given in this particular case? 680. I'm only going to do one to show you what it looks like, but we're trying to determine, so what was P hat? You told us, Erica, it was 0.482?
456.
456. So the results of one, let's say, experiment, one observation of 680 predictions, and they found that he was correct 310%, 310 times, okay? So if I just do this one time, oh, he probably didn't want to flip a coin 680 times during that animation, did it? That was probably a lot. Okay, so I can hide all of that. In one sample that I drew, I ended up with 0.494, I guess. So now I'm going to do it 1,000 total times, or 1,001. So the red vertical line represents the results from the P hat, right? That one sample that we were looking at of 360 predictions out of 680. Is that the right number? Yeah. So that was the that was what the vertical line is representing. That's P hat. And what we're trying to say is if we were to re-simulate that exact same process, right? How many times, what's the likelihood that I'm going to get the 0.456 or less, because I can get up to or less. That's what we're looking at. So in my 1,001 sampling, I only got it 7 times. I can only repeat this example or this experiment 7 out of 1,001 times. How about y'all? 11 out of 1,000? 6 out of 1,000, 14 out of 1,000, 11,
No.
9, 11, okay, 10, all right. And if you look at the decimal representation of that, every single one of us is less than 5%, right? Okay? In fact, you're pretty close to like less than 1%. Mine was less than 1%, or maybe you're right at 1%, right? Okay, 1%, only 1% of the time. So then you gotta ask yourself that proportion of samples, the probability, and this is again just a simulation, we're just looking at it, the proportion of times that I'm gonna get that exact value of 456 or less is not really something that's usual, right? It would be unusual to get results like that, wouldn't it? It would be unusual to get results like that if if his predictions were true 50% of the time. In other words, something's off, right? I can't get my results if we think the population, if we say that he's correct 50% of the time. All right. So in other words, we would say if we just wanted to look at our p-value here, okay, and I'm just gonna click this button down here for just a second, just so you know. And we'll go and we're gonna actually use StatCrunch to do this, but that p-value that I added to the bottom of it, the normal approximation there, would be the theoretical way, the calculator way of us determining the p-value, instead of using simulation all the time. Okay, I just want you all to understand what a p-value is. So when a p-value pops up and all you see is this number right here, the 0.011, we'll call it, right? That's the likelihood of getting those results or less in the long run. And it is not likely for that to happen, okay? One of the ways that we would interpret that looks like, one of the ways that that would look like, or what that sounds like when you're interpreting it, says that assuming, okay, and we'll go back to that screen really fast, assuming that the TV personality is correct half of the time, you would expect to observe the 310 out of 680 predictions in only about 1 out of every 1,000, 1 out of every 100, excuse me, if it was 0.101, 1 out of 100 repetitions of the study. That's all it means if we're trying to interpret our p-value. Okay. So what is happening here, and I put this for you on your paper right there. What we have happening here is, you know, our normal curve that we've been looking at this whole time. Okay, we have our normal curve, and we believe that under the null hypothesis, if it is true, then, right, the null hypothesis would be in the middle, okay? And we would have our observed value right here at the edge of the shaded area and the other, right? Just like we've been talking about before. Remember when we did sampling and we were trying to predict how likely was it that my sample would happen overall out of the whole population? That's all we're doing here. That's what that picture basically represents. But we're adding to that. We're saying, okay, well, if I have a 95% threshold, right? Because we keep saying something is unusual if it happens less than 5% of the time. 95% of the time it does happen, okay? And my observed statistic, right, or whatever we were looking at there in our experiment falls, let's say, in the unusual or unlikely area. This is the area that we're talking about being our statistically significant region. Okay, that's where our p-value falls. Okay, and this is how we test whether or not something has strength for or against the null. All right. So we have 3 tests that we could run. We have 3 tests that we could run, all right? The first test, which you have on your paper, the first test which you have is the left tail test, correct? The one over there on the very far left, because I rearranged this last night, all right? So when we're thinking about a left tail test, a left tail test, what we're looking at is that our alternative hypothesis is going to be less than some value. Right, now remember what parameter was. The parameter is the population's value. All right, so in a left-tailed test, we're suggesting that the alternative would be less than the populations, right? That was the test that we just ran. That he was successful in his predictions less than 50% of the time. That would be considered a left-tailed test. Now in the middle, we have a two-tailed test. And the alternative on a two-tailed test is simply this not equal. Okay, it's just a not equal. No change, not equal, something different, right? Something other than. That would be considered a two-tailed test. And then for our right-tailed test, notice the inequality on our parameter is now facing the right, in other words. So the tests that we're running, and the other thing I want you to notice is every single one of these statements for the null is a statement of equality. Every time, no matter what your test is run, we always assume the null is equal, that the null is true. So it's always going to be a statement with an equal sign. So for our two-tailed test, we're saying that it is equal versus not equal. For our left tail, we say equal versus less than. And for the right tail, we say equal versus greater than. The tails, remember how we said that something happens, less than 5% of the time? So what we're talking about with these tests is where is that 5% falling? If it's a single tail, meaning a left or a right tail test, then the 5% unusualness falls in a single tail. Everything either above my value or everything below my value, right? In a two-tailed test, the unusual observations, right, our value of unusualness gets split between the two tails. So if we had a 5% level of significance that we were interested in on a two-tailed test, we would split the unusual values 2.5% on both ends. Does that make sense? Okay, that's how they come up with these 3 different tests that we're running. That's all they mean, okay? Is where is that unusual mark? So we're gonna practice that, okay? Just remember that our null hypothesis is our statement of no difference, and it always contains an equality sign. The null is always the statement of equality, and it's always assumed to be true until we can show the alternative, right? Until we have evidence to the contrary. In other words, we seek evidence that supports the statement of the alternative. The alternative hypothesis is generally what the researchers want to show. You're assuming the null is true, but you want to show this. And whether you have evidence for or against that is what you're looking for statistically. That's our strength of evidence. So let's just kind of talk for a minute about how would you go about forming, and we'll just do it symbolically first. How would you go about forming hypotheses in these 3 examples that you have on your paper? In other words, we're going to write the null and the alternative. In 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So first of all, you need to determine, is this a proportion? Is this a mean? Is it a standard deviation that we're kind of looking at? I don't know. I have 62% in there. What variable would I assign 62%?
Your parameter.
It is the parameter. It's the population parameter. Very good. Now, what variable do I give it? P. I would give it P, right? The proportion of Americans. So P is equal to 0.62. And the other piece of information that is needed in here is that a researcher, so you want to know what is the claim? What does the researcher want to know? What do they want to know? If it's different, if the percentage is different. So the null hypothesis is always a statement of equality. So the null hypothesis says that P would be equal to 0.62. The alternative hypothesis says that it would be not equal to 0.62. It's just different. Okay, so the null hypothesis says that 62% of adults regularly volunteered for their charity work. Now, the alternative would be that less than not 62% would be equal to the charity work. Okay, let's look at the next one. According to a study published in March of 2006, the mean length of a phone call on a cell telephone was 3.25. A researcher believes that the mean length has increased since then. I always laugh at this one because I can tell how old that sentence is that I still have on there. Mainly because nobody talks on the phone anymore, it's all through text, right? Okay, so we need to decide what type of a parameter would I be using here? And what is the parameter? Mean. So what variable do I give it?
Mu.
All right. So mu is equal to 3.25 minutes. And a researcher believes that the mean length of the phone call has increased. Always looking for what does the researcher want to show? So the null is that mu is equal to 3.25, bless you. The alternative is mu is what? Greater than because it has increased 3.25. And then finally, the last question that we see there says, using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, quality control believes that the standard deviation has decreased. So what variable will I assign 0.23? Sigma, that's right. Oh, for Leo. Sigma is 0.23 ounces. So the null is what? And what's the alternative? Because it has decreased, right? It is less than 0.23. Okay, you kind of get the idea of what we're looking for here. This is your research question. This is in essence, even though it took us all semester long, this is what they start with. You got a research question and you want to know something about it, okay? Now, just real quickly, what type of a test is A? of the three test types that we had, what is the first one? The first one would be considered a two-tail. What's the second one?
Right tail.
Is that, look at the inequality symbol and where it's pointing. So that would be a right tail. What's the last one? Left tail. Again, look at the inequality symbol and where it is in essence pointing. Okay? All right. So how do I go about constructing the test, the hypothesis test? First of all, since we're focusing today on just proportions, let's just be reminded about all of the variables that we use for proportions. We know X represents the number of successes. N represents the number of outcomes or the sample size. Lowercase p is the population's proportion. P hat is the sample proportion. And we've already defined this, but alpha, which is that squirrely X, right? Alpha represents the significance level. So unless it's otherwise stated, we assume a 0.05. Okay, that's kind of the standard industry number. Okay, 0.05 assume unless other things have been discussed. And then just a reminder over there about all of the P's, right? Don't confuse a p-value with a proportion. And it just reminds you of that in your notes. All right, so just remember that when we're conducting our hypothesis test, which we call our test of significance, we are assuming the null is true and how likely it would be to get a sample proportion that is as far away or farther from our presumed probability in the null hypothesis. Okay, that's what we're doing. That's what the goal of this hypothesis test is. And then I have some procedures for you here for the testing. Number one, you have to determine your parameter. We just went through 3 examples when the parameter was not only a proportion. We're focusing on proportion today, but if you get to a test, right, or if you're doing this out in the real world, you have to determine your variable, whether or not it's a mean, a proportion, or standard deviation, which is called chi-squared test. Okay, and it is used. Verify the requirements for our normal distribution, right? In a proportion, that happens to be where we want to do the NP1 minus P, greater than or equal to 10, okay? Then you want to come up with, once you've identified your parameter, then you want to determine your null and your hypothesis statements. Then you want to see or identify, either select or identify your level of significance. Now, what we're going to continue our discussion on Wednesday is what it means to make this type 1 error, right? We're just going to practice using alpha and our tests today, and then we'll continue our discussion on this. So that's kind of what that's referring to. Then you go in and you use technology, right? StatCrunch. Everybody put a little, I'm going to use StatCrunch next to number 5. We're not going back to our Rossmann-Chance app. We're not going back to that again. We're going to use technology to find the p-value. We are focusing on the p-value. That's our way of looking at our test, but I'm going to show you the critical value method in a minute also. Okay, now what we need to know, how do we compare the p-value with alpha? So add to your notes that if the p-value is greater than or equal to alpha, we say that we are going to fail to reject F2R is fail to reject the null. If our p-value is less than alpha, then we actually reject the null. We say the null can't be that way. We'll talk about the conclusions, stating the conclusions, as we get towards the end of this. And then if you were to look at the confidence interval, you would be asking whether or not the null hypothesis is in the confidence interval. If it falls outside of the confidence interval, it's unlikely to have a null that looked like that, right? Okay, I can tell you, and I would encourage you to look at any type of medical study. Those are the easiest ones to look at. Any type of statistical study, and you will see both a confidence interval as well as the p-value given in conjunction with the results of a study. So they give both of them, all right? Okay, and then you state your conclusions. All right, so let's look at this example here. A campus legend tells the story of two friends who lied to their professor by blaming a flat tire for their having missed an exam. The professor sent them to separate rooms to take a makeup exam, and on the first question, which was worth 5 points, that was easy. The second question, which was worth 95 points, said, which tire was it? I think that'd be kind of funny. All right, so suppose a professor at MCC wanted to study the likelihood that MCC students randomly chose the same tire. So he asked his students, if you were caught in this situation when you suddenly had to choose a hypothetically flat tire, which of the 4 tires would you say went flat? So left front, left rear, right rear. All right, that's what we're looking at. Of the 28 students surveyed, 14 chose right front. Does this provide evidence that MCC students will pick the right front tire more often than others? That's what we're looking at. All right. So what's the population and the parameter? Let's choose the parameter. What's the parameter of the study? But what's the population? Let's choose that one first. All MC students, that's right. So the population would be all MCC students. And remember, the parameter is supposed to describe the population. So our parameter is basically what is the probability that you choose the right front tire? What's the probability that the right front tire is chosen?
1 out of 4.
There's only 4 tires, right? So it's a 1 in 4 chance that you choose the right front tire. So P would be equal to 1 in 4 or 0.25. Okay. What's our sample? Remember, the sample is, who is the sample? Okay, so our sample would be the 28 MCC students. And what is our statistic? Okay, and what variable can I assign that? P hat. All right, so P hat from this sample was 14 out of 28 or 0.5. Okay. So what is the null hypothesis? Let's see if we can come up with words that represents the null. The long run proportion of students that pick the right front tire. This is about what we assume to be true. What are we assuming to be true?
H naught is P equals 0.25.
All right, so in words, the long run proportion of MCC students that pick the right front tire, I'm just gonna call RFT, is 0.25. Symbolically, H sub naught says P is equal to 0.25. So the alternative what are they trying to show? What's this researcher want to show?
Section of the student sample. The right file is on file.
No. Well, yes. Well, no. The number was correct.
But it, because it's greater than.
Right, so it's more than, and I didn't know if that was what you said or not. So we have right here. Does this provide evidence that the NC students will pick the right front tire more often than others? There's our inequality symbol we're gonna use for the alternative. So the long run proportion of MCC students that pick right front tire is more than 0.25, or in other words, P is greater than 0.25. Okay? All right. Well, we've got the null and the alternative. Now let's see how we run the test in StatCrunch, okay? In StatCrunch. So from StatCrunch, you're going to go to the same location that you went when you ran the confidence interval. We're going to use the same places. So our proportion, so we go to stat, proportion, stat, one sample with summary. Same exact place. Now, the number of successes in the study or in the sample was 14 out of 28. And this time, we're going to actually use our hypothesis test for P. Now, I don't know that I put anything in there. So we're going to assume that this is running at a 95% confidence interval, or excuse me, we'll have a hypothesis test equal to this. Okay, actually just a second, I'll go off on that in just a minute. Now, when we write our hypothesis test down here, our P was equal to 0.25. We're going to change our inequality symbol to be greater than. Notice that once you put in the populations parameter, it automatically filled it in the next spot. I don't need to do anything else. I'm going to hit compute. Okay. Everybody have those results right there. Okay, so in StatCrunch, okay, I want everybody to go ahead and write down this information. What I want you to write down is this heading here, and I want you to write down both of those two rows. Use your standard error, just round to 3 places along with our z-stat, but I want you to write those numbers down on your paper so that you have them when you look back at this. And you have them on your paper, or you have them on your screen, correct? They weren't any different from mine. So I would like for you to write down those two rows. Because I want to be able to explain where this information comes from. Okay, so you're writing those down. Now, everybody should have the same thing that I have on the screen up there. P. Your count's 24, you have a total of 28, your sample proportion is 0.5, we knew that already. The standard error should be 0.082. Your z-stat is 3.05, and the p-value is 0.0011. Does everybody have that written down? Okay. So we used technology instead of a simulation to come up with the p-value, the probability of getting that statistic, right? Our sample proportion or more. What was the likelihood of us getting it? And that chance is only 0.0011. So if we're going against a 5% likelihood, right? If our level of significance is 0.05, would we say that this is an unusual? Is it unlikely to get this result? Yes, right? 0.0011 is less than 0.05, correct? Okay. So our p-value shows up here, obviously. It says p-value right there. And what we can say is that our p-value, which was equal to 0.0011, that's obviously less than 0.05, which is alpha. According to the statement we wrote up above, we would what we call reject the null. In other words, it's unlikely for us to have this result in a sample if the null were true. So we reject that that's the true value of the null. Now, some of this other information in here, just to help you understand where it kind of comes from. So this standard error right here is actually the standard deviation of our sample mean, or the standard deviation, yeah, the sample mean, right? Remember when we had, what was it? I think it was, formula was P1 minus P over N, take the square root of it. Remember that formula back in chapter 8? Remember that formula we put in? Okay, well, that's that value right there, because remember, we're trying to figure out what's the likelihood if I repeated this sample mean, what's the likelihood that that's going to occur in the larger population? That's what the standard error is giving you. The z-stat actually happens to be the z-score for our p-hat, which was 0.5. In other words, it was 3 standard deviations away from the mean. That's what that was telling us. So that z-stat is referring explicitly to what is the standardized value for my sample. Okay, it's what's the z-score for my sample. So there's 2 ways for people to do hypothesis testing. One is using that critical value right there of what we're given. And the other is using p-values. We will be focusing on the p-value, but the z-stat, there's a question, and it's like part of this question, and I can't get it out of there. And you have to identify the z-stat, but your conclusions are going to be the same, whether you're doing a z-stat or a p-value. Okay, so this is how we run it. Fairly easy. You go put the same thing into StatCrunch. You're using the same exact menu as you were before. Now, how do I make those conclusions? Okay, so this is somewhat of a chart. I couldn't get a clean screenshot of it, so it's a little fuzzy, but it goes along with what we've been talking about, right? And notice that all we're doing in here is evaluating the p-value against alpha at 1%, 5%, or 10%. And based on wherever it falls, is all you're doing is changing your language as far as there's very strong evidence, moderate evidence, some evidence, or no evidence against the null. So the p-value allows us to quantitatively, like numerically, come up with a number that evaluates the strength. Okay? And all we're looking at here is, and again, we talk more about this tomorrow, when we are talking about the null, when we are stating our conclusions, we never state the conclusion in terms of the null. We actually always state it in terms of the alternative. So I've given you, I want you to highlight this part right here. I have given you a fill in the blank for how you will go about making your conclusion based on the p-value results, whether you fail to reject or reject. There either is or is not sufficient evidence to conclude that, and then you insert your alternative. So our conclusion, based on our problem we were just looking at, says that we rejected the null, correct? For our, whatever we were looking at here, the flat tires, right? We rejected the null. So this would look like there is sufficient evidence to suggest that the number of students who pick the right front tire is more than 2.25. I restated the alternative. Now we'll talk about how you can remember that when we come back to class, but we're gonna stop there because we don't have any more time. We'll pick up with this lesson when we come back, talking about what happens when you make errors, and then picking up how to go about doing a mean testing. So make sure you bring this paper back with you. All right, y'all have a great day. I'll see you next time.